Hey there! Have you ever stopped to wonder what's really going on when a piece of metal rusts? Or how about when you bake cookies? I mean, the world around us is just constantly changing, right? Well, today, we're going to pull back the curtain on the magic behind all that stuff. We're talking about chemical reactions.
So let's just jump right in. Think about this. A rusty nail, a warm, gooey cookie, and the very air you just breathed out. What could they possibly have in common? They seem totally different, right? But they all share this deep, fundamental secret. It's a hidden process that explains how stuff turns into, well, other stuff. And stick with me, because by the end of this, you're going to know exactly what it is.
All right, so here's the game plan for today. First, we're going to learn how to spot these chemical changes out in the wild. Then we'll get into the language scientists use to talk about them. After that, we'll uncover this huge fundamental rule of the universe that governs all reactions. Then we'll get into sorting them into different types. And finally, we'll bring it all back home, to things like rust and even your own breathing.
Okay, so remember that big secret I mentioned? The thing connecting the nail, the cookie, and your breath? Well, here it is. They're all the results of chemical reactions. That's it! A chemical reaction is really just a process where one bunch of chemical stuff turns into a different bunch of chemical stuff. And the cool part is, you don't need a fancy lab or a white coat to see it happening. You just need to know what to look for.
And you know what? The clues are actually super simple. There are four main signs that something chemical is going down. First, a change in state, like a liquid becoming a solid. Second, a change in color. That's a classic one. Third, you might see gas being created. Think bubbles. Bubbles are a huge giveaway. And last, a change in temperature. If you've ever cracked open one of those chemical hand warmers, you've literally felt a reaction happening. So yeah, those are the big four signs to keep an eye out for. So, spotting a reaction is one thing, but how do you, talk about it or write it down? Writing out a full sentence every single time is just, well, it's a pain. It's clumsy. So chemists came up with a better way. They developed this really powerful shorthand to describe what's happening, and it's super clear and efficient. Just look at this sentence, for example. When a magnesium ribbon is burnt in oxygen, it gets converted to magnesium oxide. I mean, it's correct, but wow, that is a mouthful, isn't it? Can you imagine having to write that out over and over again for a complicated process? No way. There's got to be a better way to do this. And of course there is. This is what we call a word equation. See how much cleaner that is? So the stuff on the left, the magnesium and oxygen, we call those the reactants. That's your starting lineup. The arrow just means turns into, and the thing on the right, the magnesium oxide, that's your product. That's what you get at the end. Pretty simple, right?
But we can make it even shorter. This right here, this is a proper chemical equation. We just use the chemical symbols for everything. Mg for magnesium, O2 for oxygen, and MgO for magnesium oxide. This is the absolute shortest, most useful, and universally understood way to show what's happening. This is the real language of chemistry.
Okay, so now we have our chemical sentences. But just like any language, you can't just throw symbols around. There are rules, and in chemistry, there is one rule to rule them all. It's not just about making things look tidy. This is about following a basic, unbreakable law of the entire universe.
In that law, it's called the law of conservation of mass. And the idea is actually really simple, but it's also incredibly profound. Basically, you can't just create matter out of nothing, and you can't make it disappear into thin air. Whatever atoms you start with, you have to end with the exact same atoms. They can shuffle around, bond with new partners, make new molecules, but they are all still there. Nothing gets lost. Seriously, this one idea is the foundation for everything.
So let's take a look at this reaction for rust forming. We call this a skeletal equation. It's just the basics. But if we actually count the atoms, Houston, we have a problem. See? We start with one iron atom on the left, but we magically end up with 3 on the right. And we start with 1 oxygen, but end with 4. Where do they come from? This equation, right now, is breaking that huge law we just talked about. It's wrong. It needs to be fixed. It needs to be balanced.
Honestly, balancing an equation is kind of like solving a logic puzzle. It's a step-by-step process. You see, we can add big numbers out in front of the molecules. We call those coefficients. You can't change the little numbers, just the big ones. So we start with the messiest looking molecule, Fe3O4 in this case, and we just go element by element. First, we tackle the oxygen, then the hydrogen, and then the iron, until everything adds up. Let's see what it looks like when we're done.
And boom! Look at that, it works. 3 iron atoms on the left, 3 on the right.
8 hydrogens on the left, 8 on the right. 4 oxygens on the left, 4 on the right. Everything lines up perfectly. It's totally balanced. This is just a perfect example of that law in action. No atoms magically appeared or disappeared, they just got rearranged. This is how you write a correct chemical equation.
All right, so we know how to write them, we know how to balance them. Now we can start sorting them into different categories. Think of it like a biologist classifying animals. Chemists do the same thing with reactions, grouping them together based on the patterns they follow. And this is super useful because it helps us predict what's going to happen when we start mixing things together.
So the two most basic types are basically opposites of each other. First, you've got your combination reaction. That's where two or more simple things get together to make one bigger, more complex thing. You know, A plus B makes AB. And then you have the exact opposite, a decomposition reaction. That's where one big thing breaks apart into smaller, simpler pieces. So AB breaks down into A and B. Simple, right? One builds up, the other breaks down.
And get this, you are literally powered by a combination reaction as we speak, right now. It's called cellular respiration. Your body takes glucose, that's sugar from your food, and combines it with the oxygen you're breathing in. And what comes out? Carbon dioxide, water, and the most important part, all the energy that lets you think, move, and even listen to me right now.
Now, for the other side of the coin, decomposition. This happens all the time in huge industrial processes. For example, when you heat up limestone, its fancy name is calcium carbonate, it breaks down. It decomposes into something called calcium oxide, or quicklime, and it releases carbon dioxide gas. And that quicklime? It's a critical ingredient for making cement. You know, the stuff that basically builds our entire modern world.
Okay, next up, we have displacement reactions. Think of this one as a chemical swap meet, a trade. In this classic experiment, you drop an iron nail into a bright blue solution of copper sulfate. Now, it turns out iron is more reactive than copper, so it basically just shoves the copper out of the way and takes its spot in the solution. And the result is so cool, the nail gets coated with a layer of pure copper, and that blue solution starts to turn clear. A perfect swap.
All right, for our last section, I want to zoom in on one specific type of reaction that is, and I'm not kidding, happening everywhere, all the time. It's behind the energy in our bodies, it's why food goes bad, and it's responsible for metals falling apart. We're talking about the slow burn of oxidation. Now, here's the key thing to get about this. Oxidation and another process called reduction, they're a package deal. They always happen together. So a simple way to think about it is that oxidation is when something gains oxygen. Reduction is when something loses oxygen. They're two sides of the same coin. You can't have one without the other. If something is gaining oxygen, something else has to be losing it. That's why chemists just mash the words together and call them redox reactions.
And this brings us right back to where we started. That rusty nail? That's just a common type of corrosion. It's nothing more than the slow oxidation of iron. And when the fats in your chips or nuts go bad and get that funky smell, that's called rancidity. And yep, that's oxidation too. See? These aren't just some weird concepts from a textbook. They're happening in your kitchen and in your driveway every single day.
So, from the combination reactions firing away inside your own cells to the slow oxidation happening on a rusty old gate, our world is just this incredible symphony of chemical changes. And now that you know the language, the rules, and the patterns, you can start to see them everywhere. So I'll leave you with this. The next time you see something change, anything at all, just stop and ask yourself, what invisible reaction is shaping my world right now? Thanks for tuning in.